F Ernie was, you said 255. Okay. And so he's accelerating at 3 meters per second squared over frictionless snow. Some good snow. Or it's terrible snow because it's ice. If Ernie and Bert hit a patch of bare concrete that exerts a force of friction of 180 newtons. So now, instead of just Ernie's forward applied force, F Ernie of 255, we've got gravity and a normal force. We're now going to add to it a force of friction backwards of 180 newtons. So, practically speaking, if you had to think about what was happening, what does your intuition tell you is going on? Anybody. This is not just for Angelina. Yeah.
Like just describing what's happening.
Yeah, what's going on? What does your intuition tell you should happen?
Okay. They just came off the snow. They've hit a rough patch of concrete. The concrete's gonna kind of slow them down pretty rapidly. So,
Possibly. Possible. Okay. Look at the forces that are in play here. We went from having just this in part A to this now in part B. What direction is my net force on Bert? Still going to be to the right. Why? So we're going to call this direction positive. It's going to be F Ernie minus the force of friction, because this is still bigger than, well, if I call this direction positive, it's always going to be positive minus the opposite direction. So it's going to be 255 minus 180. So it's going to give me an F net of what? Sorry? 75? Seems reasonable. And that's still positive. So my F net then is going to be to the right. So then the question is, what is their acceleration going to be over that concrete? Well, we know F net is not just the sum of the forces, it's also equal to your mass times acceleration. So the mass of, do we know what the mass is?
75 equal to 85 times 80.
Thank you, Luis. The mass of Bert and the sled was 85. So the acceleration is now what?
A equals 0.8 joules.
And that value is positive, so the acceleration is which way?
Right.
To the right. So we're still accelerating to the right. We're just not accelerating quite as quickly. Ernie's force hasn't decreased at all, but the usefulness of it has. But Bert is still accelerating to the right. So in fact, Connor, unfortunately, the concrete has not slowed them down. They are still accelerating. Angelina, does that make sense? Okay. And there was only 1 meter per second squared answer there on that sheet, so it's got to be it. And it's bang on. So that's 4B. We were good at the rest? Can I do 6? Physics teacher attaches a 4 kilogram brick to a light string. Pulls straight up. The brick accelerates upwards at 3.2 meters per second squared. How much force did the teacher apply to the brick? Okay, so 6. Let's draw the thing. I have a brick. I have a string attached to the brick. What else is acting on this thing? Oh, a string is what kind of force? Tension. So I like to call it F sub big T. You can also, some people also call tension big T, but tension big T is also going to be period in a little bit here. Period is the length of time it takes for something to happen once. So I don't like to use big T. I use F sub T. What else is acting on my brick? We got gravity. We know that the brick weighs 4 kilo, or the, sorry, ooh, no, bad. The mass of the brick is 4 kilograms. So Fg is going to equal 4 times 9.8, which is 49 newtons. Makes more sense. We also know that this thing's accelerating upwards. At 3.2 meters per second squared. So we have to call some direction positive. You want to call up positive? Why?
Just moving to its final destination. I don't know.
Okay. Sure. It doesn't really matter which way we call up. We just then have to be consistent. Oh, sorry. It doesn't matter which way we call positive. We just have to be consistent. If up is positive, then this acceleration remains positive. So then I just need to find my tension force here. Every problem in this section is going to start with this. Well, almost every problem in this section is going to start with F net equals MA. What is F net in this case? F net is the sum of my forces acting in the direction of motion. It's going to be Ft minus Fg equals Ma, and now I can start to fill in those values. Ft minus 39.2 equals 3.2 times 4. That's A, that's M. I had them backwards. So then Ft is going to be, I'll just write it in the proper order this time, 4 times 3.2 plus 39.2. So it's going to be 12.8 plus 39.2. That's the only one small, that's the only answer small enough, so I'm going to assume that that's correct. The tension force then must be 52 newtons. Jasmine, that make sense? Okay. Okay, so that's Newton's second law. Love it. We good with the rest of these? I don't really want to do all 4. But. Okay, then flip the page. Grab your notes if you haven't already, and let's move on. We are going to talk about the last of Newton's laws today. The best one. It's debatable. I could see why some people would think that. Mathematically, it's the easiest because there really is no math here. Practically, it's the most entertaining, and it's one that we don't really like. The intuition here is going to be a difficult one to wrap our brain around, perhaps as well. I'm just going to pull all of these out because I've used all of them except yellow. Okay, so Newton's third law. Our first law was what? What was the first law? It is inertia, yes. An object in motion or at rest, whatever its motion is, will remain doing what it's doing, either moving or not, unless what? I think someone else said. Someone said it. Who said it? Net force was number 2. Unless some force is applied to it. Yes. You could say that unless a net force is applied to it, but unless some force is applied to it. That's the first law. Second law. A net force produces an acceleration, which is, if you go on and take physics in the future, you will eventually be told that, like so many other science classes, you will be told, yes, your physics teacher actually lied to you. That isn't technically Newton's second law. Newton's second law actually invokes a concept we're not going to talk about in Physics 11 called momentum. You're going to do momentum in Physics 12. But for the sake of what we do, a simple understanding of Newton's second law is that a net force produces an acceleration. The third law, I'm willing to bet you've all heard of. Luis, what is it?
Every action has a reaction.
For every action, and it's more specific even than that. That's really hard to read. For every action, let's go dark blue. And when I say action, I want you to think force. For every action, what? There's an equal and opposite reaction. That word's important. That's also important. Okay? For every action, there is an equal and opposite reaction. Now, how these things show up practically is going to be functionally different. But we need to recognize that this is true. For every action, there is an equal and opposite reaction. Any interaction between two forces, any interaction in, there should be a word here, that involves two, oh, wow, maybe not. Oh, sorry, that's not true. It was good the way it was. Any interaction involves two forces that we call action reaction forces. Comes straight from the law. And these pairs of forces always act on both objects. So, you hit a baseball with a bat. What are the two forces involved here? Or what are the pair of action and reaction forces here? Oh, sorry. I'll tell you what. Oh, maybe, no. Luis, what do you think?
I think the applied force of the ball, but there is a normal force that reacts with the same amount of newtons in the bat and in the ball, but the bat has more mass and it's more solid, so it's more like the mass is bigger, so the reaction is not like that. You can't notice the reaction that much in the bat, but the ball has less mass and it's less resistant, so it's go like far away from the hit point.
Yes, everything that Luis just said, I've got to somehow now fit here nice and easy. You hit a baseball with a bat. So there's two things that are happening here. First of all, the bat hits the ball. And as Luis said, underneath it, I'm going to just give kind of a brief explanation of what he was talking about here. The ball mass is typically much, much smaller than the bat. Batmas. It's like Christmas, but not. If I put a second S there. And so hands up if you ever hit a ball with a bat. Like at a high-end level, not just like a pitcher's throwing it at you and you connect. Okay, a few of us. Do you feel it in the bat? You can. If you're playing high-end ball or even moderate high-end baseball, a good pitcher, you're going to feel vibration, like it can hurt your hands if you're not holding the bat tight enough. So the bat, not only does the bat hit the ball and the ball goes flying, the ball also hits the bat. But because the ball's mass is much, much smaller than the bat's mass, the ball flies away. Well, the bat just vibrates. But both of those things connect with each other, and we have to acknowledge that that happens. A sprinter running, what's actually happening here? How does a sprinter, or even when you walk, how do you move forward?
Move your legs forward and backwards and push yourself kind of forward.
But how? Manuel.
When you push into the ground, you move again.
Okay, so you push back on the ground. The ground pushes forward on you. This is not just true for sprinters. This is true for anyone who's ever tried to walk anywhere, ever. Like how you got from the parking lot to my classroom. Interestingly enough, what is pushing you forward? What force specifically? Normal force pushes perpendicular. So if normal force was pushed to the surface, so if normal force was pushing you, it would throw you into the air. Can't be normal force. It's got to be friction. You're pushing back, but your foot's not slipping. So if it's not slipping, that must mean there's a friction force. So the friction's actually what propels you forward in this case. So friction's actually acting in the direction of your overall motion, but it's opposing the backward motion of your foot. It's interesting. Traction increases friction. Traction, when we talk about friction, I've mentioned it once already, but we're going to talk about something called the coefficient of friction, which is a property that exists between two materials. And increasing traction increases that value for the coefficient of friction. So if you're going running in bowling shoes, for example, versus running in cleats, your traction is going to be fundamentally different because the coefficient of friction between turf and those two types of shoes is going to be radically different. Bowling shoes are designed to have zero traction. Cleats are designed to have maximum traction. So yeah, that's how traction and friction are related. A fish swimming through the water. What forces are acting there? Yeah.
Fish is pushing the water.
Fish pushes water. And then water then, to move forward, must push the fish.
By the way, there's Newton's law. The one you can notice in your like corpus questions that you like to do, right?
Say that again.
The car crashes and corpus questions that you like to do. You see this.
Oh, absolutely, yeah.
Yeah.
Yeah, absolutely. So imagine, let's take a really extreme example here. We've got a bug hitting the windshield of a semi. No one really likes bugs, so no one really seems to get broken up when I kill bugs. Bug hits the windshield of a semi. What's the force pair?
Windshield hits bug, bug hits windshield. Bug has smaller mass.
There we go. Okay, so windshield, hold on though, hits bug. Bug hits windshield. Which force is bigger?
Windshield.
You understand?
Okay, so which one of them is right?
One is support. Windshield's accelerating. The mass is bigger.
The question says, which force is bigger?
Because it's an equal reaction, but the mass is
Yeah, this goes, what is Newton's third law? We have to hang on to what these laws are. For every action, there is a equal and opposite reaction. So the windshield hits the bug. The bug hits the windshield. Which force is bigger? Luis is right. They have to be the same. Okay, so we have F of the windshield, and we've got F of the bug. The forces have to be equal.
How come they make special proportions to run someone over and how come both of them don't like fall backwards? Because one could have more ability to like hold their ground.
So that's kind of what my next question is going to be, but in the context of this question here, what then is the issue? Because we all know what's going to happen to the bug in the end. The bug's going to exist as a fine mist in like a million pieces of vapor on the windshield. Someone flicks the switch, the windshield goes, smears the bug, bug's gone, right? So what's the issue here? If forces are equal, what's causing so much damage to the bug? Its mass is not,
the resistance like
its mass is going to play a part in it.
One of the bugs was like this. Its contact, its mass is so small that it can't
Okay, someone give me a bug that they hate. A flying bug that they hate.
Fly. Like a fly, like a bug.
Oh yeah, wasps. We hate wasps.
Oh yeah, those suck.
Okay, mass of a wasp.
When it hits our windshield, just
Okay, the average weight of things. Oh wow, they're really light. Perfect. 20 milligrams. Okay, we're going to a queen wasp because screw them. 25 milligrams. Okay, so we're going to do some math. The bug is a wasp in this case. 25 milligrams, which is what in kilograms? 25 milligrams is 25 times 10 to the negative. Milli is 10 to the negative 3 grams. So that's going to be 0.025 grams. So how many kilograms is that? I believe you're correct, sir. Okay, so there's our bug. Now, the windshield is not so much an issue because the windshield, windshield's certainly problematic. But the bigger issue is what's the windshield connected to? Nope, a semi. Now, a mass of a loaded semi yeah, it really is. The maximum legal weight for a fully loaded semi in the United States is 80,000 pounds. So that's 36,000 kilograms. Okay, the truck is going to be 36,000 based on a direct conversion. 287, that'll make it 288 kilograms. Okay, so what's the problem here? The bug is nowhere near that. So I don't necessarily know what these two forces are, but we can talk about them a little bit here. The forces, they're going to be equal, whatever they are. The mass of the truck, remember here, F equals ma. So if this thing has a, I don't know, let's put a value in here for the force. We're just Googling some values here. That's not a force, though.
No, but you would get your acceleration. Let's say if you go from 0 to 60, that way.
Oh, you want to work it backwards. Interesting. Okay. Okay, so well, let's talk it through this way. If I have 36,288 kilograms times my acceleration, and I've got F equals ma going over here for the bug, 0.000025 times a, that's going to be for a bug, and this is going to be a truck. If these forces are going to be equal, oh, sorry, I can zoom this in so it's easier to see those numbers. If these forces have to be equal, which of these accelerations has to be larger? The bugs. Much, much, much larger. Because we're talking on the order of a million. There's a million times difference here between the acceleration and almost a million, maybe 100,000 times the difference between the truck and the bug. So is the truck going to even notice the impact of a single wasp? No. Is the bug going to notice the impact of a single semi-truck?
Yes.
Yeah, you betcha. And it's not necessarily the force that kills you. It's the acceleration that the force causes that's going to mess you up. In this case, the bug.
You mean like the acceleration as it's just slow, and it goes from like a positive, like to an instant, like negative.
Yes, that's exactly what I mean. As the bug is flying forward, it'll have probably no acceleration. It's just going. And now all of a sudden, it has a massive negative velocity. To do that, you need a massive acceleration. It's the acceleration that's going to mess this bug up. Because, well, and Luis loves to talk about inertia. So we can talk about the inertia of all the parts of the inside of the bug. The insides of the bug want to keep going forward, but the outside of the bug's now going the other direction. Yeah, splat. This is ultimately the problem. It's not necessarily the force that hurts you. Because the truck didn't experience anything. The truck didn't even crack a windshield. Next one, example. A couple more. Recoil. Anyone ever shot a gun? Hands up. Okay. Like an actual gun. Okay.
Water gun,
Not a water gun. So talk to me about what's happening here with recoil. For those of you who have fired a firearm, what's it like?
kind of pushes back into your shoulder.
Pushes back into your shoulder, assuming you're firing a rifle. Okay. So what's causing the gun to slide backwards into you?
As the bullet is shot, depending on how it's shot, it moves forward, and depending on what kind of gun it is, it moves at a very, very high speed, very, very quickly.
The bullet, you mean?
So, yeah.
Okay.
And so when you have that reaction, as it's shot, there's a very tiny point in the gun where it goes 0 to like very fast.
Yeah, but simple. Okay, so in order for the bullet to be moving forward,
Yes.
it has to be pushing against something.
Yes.
In this case, what it's pushing against is an expanding cloud of gas. But that expanding cloud, because the gunpowder ignites and it creates, that's what's causing the bullet to fly forward. It's expanding gas. So that expanding gas, though, is also then going to push backwards on you, because the bullet is blocking it from just blasting out the front of the gun. So to simplify it, the bullet pushes back on the gun. As the gun pushes forward. On the bullet. And so if you've never fired a gun, perhaps you don't recognize that there was a recoil there. And depending on the caliber of the weapon, the recoil is going to be different. A .22, for example, is going to have a very small recoil. Also relatively small. An AK, yeah. As opposed to a rocket launcher, where you need to be kneeling on the ground, mounting that thing to your shoulder and able to fire it properly. But a rocket launcher's also got a big hole out of the back to reduce the recoil. Well, I could, maybe, do I show you a video? Do we want to see a video?
Yes.
Okay, I'll show you a video. If I still have it on here. No, I don't have a video in RPG. Unless I got rid of these videos. I hope I didn't. It's before my daughter was born. I didn't expect to show you this video today.
It's better than you are.
It's better than I am?
Yeah. Is it the potato gun?
No, it's not the potato gun. Oh, here it is. Okay, so this.
Oh, he's firing guns.
That's me. That's me. At a firing range. Yeah.
His plaid
My plaid shirt. Normally, apparently, this gun is not supposed to be. Oh, I have a slow motion video of the same thing. Actually, my wife's is better. Here, this is my wife. This one's in slow motion, so it'll take a little bit. Waiting for it. It's coming. There, that is a great example of the recoil of firing a gun. Yeah, well, that's exactly what that was, actually. That was a Desert Eagle. That was a lot of fun. But a great example of what recoil can look like. And, I mean, my wife is a lot smaller than I am. The first video I showed you, that was me firing that same handgun.
Like this, in that case, it's like all about your wrist.
Yes. Yes, and so the way I was holding it, it went straight back as opposed to the way my wife was holding it. Yeah. It's a heavy gun, too. Bricks. Buddy smashing bricks. What's the force pair? Real easy.
Like force equals the normal force.
Oh, no, even simpler. We're not doing any math here. Just what's the pair? The man hits brick. What we often don't think about, though, is that the opposite is also true. The brick hits back. Brick hits man. Okay. And this is often what freaks people out, because we know it's going to hurt. Well, why does it hurt? You hit the brick. That's not the issue. That's going to damage the brick. What's going to happen is the brick's going to turn around and smack you back at the exact same time. This is what hurts you. If you've ever punched a wall, you know it's painful. Why? Because the brick hits you back with the same force that you hit it. Why then can someone smash through a brick and not break their hand versus punching a brick? If it doesn't break, the hand breaks? No, what's happening? What's the difference? What's the fundamental difference? He's breaking it. So the acceleration of the hand is going to be less than if, which is counterintuitive, right? So you want a force big enough to break the brick to decrease the deceleration of the hand. If you don't hit it hard enough, your hand slows down too fast, and it'll break your hand and not the brick, which is counterintuitive, which is what freaks people out when they're training to do martial arts in the first place. The force needs to be big enough so that your acceleration slowing you down is less, because the breaking of the brick actually extends the time. You have to be hard enough to beat the brick.
And then you're fine.
Yes.
And you're in the right spot. Okay.
And hard enough. And then rockets. Rockets are similar to bullets. The rocket pushes on exhaust gas. That same gas pushes on the rocket. But some people would say, well, isn't this just pushing on the air? Is it pushing on the air? Well, rockets work in space, right? There's no air in space. So it has nothing to do with the atmosphere of the launch of the rocket. It has everything to do with just the force on the exhaust gas, which is exactly what's happening here. I just simplified it with the bullet in the gun. So that's it. That's Newton's third law. I want you guys to do a few things with the time that remains. There are, I think there's 5 questions on this 2 pages. There's 1, 2, there's 4. There's only 4. I want you to do those 4 questions, either alone or talking through your people sitting around you. And then what I want you to do, to lead into tomorrow's lesson on gravity, and I have not forgotten to show you the video about how gravity is not true. I'm going to show you it either it'll be tomorrow. I want you to, after you finish those first 4 questions, I want you to grab a computer at the back, and I want you to open up another gravity simulation. This one's not about Fg equals mg, it's about gravitation between larger objects. Yes, so like the gravitational pull between Mr. Lackle and me right now, because he's right there at the back of the class. Mr. Lackle, what's going on? How you doing?
Hey, so I wanted to play a game with my student teacher, 2 good teachers and a dud, and see if she could spot them. So I was wondering if she could come in and observe you.
Ooh, am I the dud or am I the good teacher? Sure.
Yeah, you're on.
What block?
This block.
Like right now?
No, no. Just for maybe next week or something.
Sure.
So just come in, just watch.
Sure.
How you guys, see how an awesome class looks.
Huh. She can come into any one of my blocks, just not D because I have a prep, and that would be.
This block.
Okay, sure. Sure.
Everybody.
Works for me.
What's that?
Works for me.
Appreciate that so much.
No worries, man. Happy to help.
You're not the
Well, who knows? Depending on the day, I might be.
Wait.
See you later. He's just putting himself down and building me up. Okay, so that's what you're doing the rest of class. Take a look at these 4 questions, reason them through, and then when you're done, grab a computer. I want you to head to Google. You're going to Google PhET Gravity Lab Simulation. It will be fairly straightforward to find, and then you're going to go through it, play with some gravity, and then we're going to learn about gravity tomorrow. Your guys' quiz on Newton's laws is going to be on Friday. I'll tell you right now, you're going to have to tell me what the laws are. So, that's a thing. Among other things. So there you go. On your mark, take care.